The atom is a paradox. It is a tiny, almost inconceivably small particle, yet it holds within it the secrets of the universe. It is the fundamental building block of all matter, the very essence of everything we see, touch, and experience in the physical world. Yet paradoxically, it harbors the power to destroy civilization, to unleash forces so destructive that they can wipe out entire cities in an instant. This duality lies at the heart of the Nuclear Energy Saga, a tale of immense potential and equally immense danger. It is a story of scientific breakthroughs, technological marvels, and the enduring challenge of harnessing the atom's awesome power for the benefit of humanity. From the early days of atomic theory to the cutting-edge research of today, the journey has been nothing short of extraordinary. This is a story of immense promise and grave peril, a delicate balance between progress and catastrophe. It is a story that continues to unfold before our very eyes as we navigate the complexities of nuclear energy in an ever-changing world. From the discovery of radioactivity by pioneers like Marie Curie, to the development of nuclear weapons during the tumultuous times of World War II, and the ongoing quest for clean, sustainable energy, the atom has captivated our imagination and challenged our ingenuity. The atom has been a source of inspiration and a subject of intense study, driving scientists to unlock its mysteries and harness its potential. It has fueled our dreams of a future powered by limitless energy, where the atom's power is used for the betterment of all humanity. Yet, it has also haunted our nightmares with the specter of nuclear annihilation, a reminder of the destructive potential that lies within. The story of nuclear energy is a testament to the boundless potential of human curiosity and the profound responsibility that comes with unlocking the secrets of the universe. It is a narrative that underscores the need for wisdom and caution in the face of great power. It is a story that forces us to confront the ethical dilemmas of scientific progress and the enduring question of how to wield great power responsibly. The debates and discussions surrounding nuclear energy are as relevant today as they were decades ago. As we delve into the fascinating and complex history of nuclear energy, we will uncover the moments of triumph and the instances of tragedy that have defined this journey. We will explore the scientific discoveries, technological innovations, and political decisions that have shaped our relationship with this powerful force of nature. The interplay between science, technology, and politics has been crucial in determining the path of nuclear energy. We will examine the triumphs and tragedies, the promises and perils that have come to define the nuclear age. From the construction of nuclear power plants to the devastating accidents like Chernobyl, each event has left an indelible mark on our collective consciousness. Join us as we embark on this journey through the nuclear age, a journey that continues to shape our world and our future. The quest to understand the atom began in the late 19th century with a series of groundbreaking discoveries that would forever alter our understanding of the universe. During this period, scientists were driven by an insatiable curiosity to uncover the fundamental building blocks of matter. Laboratories buzzed with activity as researchers conducted experiments that would lay the groundwork for modern atomic theory. In 1895, Wilhelm Röntgen discovered X-rays, a mysterious form of radiation that could penetrate solid objects. This unexpected discovery was made while he was experimenting with cathode rays, and it opened up a new realm of possibilities in both science and medicine. X-rays allowed scientists to peer inside solid objects, revealing structures that were previously hidden from view. This discovery ignited a wave of scientific inquiry that would soon lead to the discovery of radioactivity. Scientists around the world were inspired to investigate the properties of these mysterious rays, leading to a deeper understanding of atomic structure and the forces at play within the atom. In 1896, Henri Becquerel discovered that uranium salts emitted a similar type of radiation, which he called uranic rays. This was a pivotal moment in the study of atomic physics, as it suggested that certain elements were inherently unstable and capable of emitting energy spontaneously. This discovery was further explored by Marie Curie and her husband Pierre, who coined the term radioactivity and identified two new radioactive elements, polonium and radium. Their meticulous research involved isolating these elements from tons of pitchblende ore, a painstaking process that demonstrated their extraordinary dedication and scientific rigor. Their pioneering work laid the foundation for our understanding of the atom and the immense energy locked within its core. The Curie's discoveries not only advanced scientific knowledge, but also had practical applications such as in medical treatments using radium. Albert Einstein's famous equation, E equals mc squared, published in 1905, provided the theoretical framework for understanding the relationship between mass and energy. This elegant equation revealed that mass could be converted into energy, a concept that was revolutionary at the time and has since become a cornerstone of modern physics. This equation revealed that even tiny amounts of matter contain enormous amounts of energy, a concept that would have profound implications for the future of nuclear energy. It suggested that if scientists could unlock the energy within the atom, they could potentially harness a powerful new source of energy. The discovery of nuclear fission in 1938 by Otto Hahn and Fritz Strassmann marked a turning point in the history of nuclear energy. Their experiments showed that splitting the nucleus of an atom released a tremendous amount of energy, far greater than any chemical reaction. Fission, the process of splitting an atom's nucleus, released staggering amounts of energy, far exceeding anything previously observed in chemical reactions. This discovery not only advanced scientific understanding but also had immediate practical implications, leading to the development of nuclear reactors and atomic bombs. This discovery paved the way for the development of nuclear weapons and the harnessing of nuclear energy for peaceful purposes. The ability to control and utilize the energy within the atom has had a profound impact on the world, shaping the course of history and opening up new possibilities for the future. The outbreak of World War II cast a long shadow over the development of nuclear energy, propelling it from the realm of scientific curiosity into the arena of international conflict. The Manhattan Project, a top-secret research and development program launched by the United States in 1939, brought together some of the world's brightest minds to develop the first atomic bomb. Driven by the fear that Nazi Germany might develop the bomb first, the Manhattan Project poured enormous resources into harnessing the power of nuclear fission. The project culminated in the Trinity test on July 16, 1945, in the desolate landscape of New Mexico. The world's first atomic bomb detonated with a force equivalent to 20,000 tons of TNT, forever altering the course of human history. The atomic bombings of Hiroshima and Nagasaki in August 1945 brought a swift end to World War II but ushered in the atomic age, an era defined by the chilling reality of nuclear weapons and the potential for global annihilation. The use of atomic bombs against Japan unleashed a wave of horror and moral outrage, sparking a debate about the ethics of nuclear weapons that continues to this day. Section 4. From Weapons to Power Plants. In the aftermath of World War II, as the world grappled with the implications of the atomic age, a new chapter in the nuclear energy saga began. Scientists and policymakers recognized the potential of harnessing nuclear energy for peaceful purposes, offering a seemingly limitless source of power to fuel a rapidly growing world. The world's first nuclear power plant, the experimental breeder Reactor 1, began generating electricity in Idaho in 1951. This marked a pivotal moment in the history of nuclear energy, demonstrating its potential to provide clean and reliable electricity to homes and businesses. Over the following decades, nuclear power plants proliferated around the globe, particularly in countries with limited fossil fuel resources or a desire to reduce reliance on coal-fired power plants. Nuclear power plants offered a compelling solution to the growing demand for electricity. They could generate vast amounts of energy from relatively small amounts of fuel, and their operation did not produce greenhouse gases that contribute to climate change. Section 5. The Shadow of Nuclear Disasters. The promise of clean and abundant energy offered by nuclear power came with inherent risks. While nuclear energy has the potential to provide a significant portion of the world's electricity with minimal greenhouse gas emissions, the dangers associated with it cannot be overlooked. The radioactive materials involved in the nuclear fuel cycle pose significant dangers to human health and the environment if not handled and disposed of properly. These materials remain hazardous for thousands of years, requiring secure and long-term storage solutions. The specter of nuclear accidents with the potential for catastrophic consequences cast a long shadow over the nuclear power industry. Even with stringent safety measures, the possibility of unforeseen events leading to disaster remains a constant concern. The 1979 accident at the 3 Mile Island nuclear power plant in Pennsylvania, while not resulting in any direct fatalities, shook public confidence in the safety of nuclear power. The partial meltdown of the reactor core led to the release of a small amount of radioactive gases, causing widespread fear and uncertainty. The incident highlighted the potential for human error and design flaws to lead to catastrophic consequences. It underscored the need for rigorous safety protocols and continuous monitoring to prevent such occurrences. The 1986 Chernobyl disaster in Ukraine, the world's worst nuclear accident, exposed the devastating consequences of a major nuclear meltdown. The explosion and subsequent fire released a massive amount of radioactive material into the atmosphere. The explosion and fire at the Chernobyl plant released a massive amount of radioactivity into the atmosphere, contaminating a vast area and causing widespread health problems. The disaster led to the evacuation and resettlement of over 300,000 people and had long-term effects on the environment and human health. The 2011 Fukushima Daiichi nuclear disaster in Japan, triggered by a tsunami, further underscored the vulnerability of nuclear power plants to natural disasters. The earthquake and tsunami caused a series of equipment failures, nuclear meltdowns, and the release of radioactive materials. The Fukushima accident reignited concerns about the safety of nuclear power and prompted many countries to re-evaluate their nuclear energy programs. It led to increased scrutiny of existing plants and a push for more robust safety measures to protect against future incidents.